The mystery of 3 Atlas deepens as it approaches the Sun. From the far reaches of interstellar space, a visitor is advancing toward our solar system and is challenging everything we believed we knew about comets. Astronomers call it 3I Atlas, the third interstellar object ever detected. And every new piece of data arriving from observatories reveals something no one expected. This body, discovered by the Atlas system in Hawaii, moves at a speed exceeding 100,000 kilometers per hour with a hyperbolic trajectory that confirms it comes from beyond our cosmic neighborhood. But what has most surprised scientists is not its speed, but its unpredictable behavior. In recent weeks, its brightness has varied unusually, as if it were breathing. Its color, an intense bluish-green, indicates a composition rich in cyanogen and diatomic carbon, elements that react curiously to solar radiation. Telescopes like the Vera Rubin and the James Webb are following its path, seeking answers. Why does its luminosity increase and fade in irregular cycles? Why does its acceleration seem not to depend solely on solar gravity? The mystery grows deeper as 3I Atlas approaches its closest point to the Sun. Whatever happens in the coming months could offer the first direct look at an object formed in another stellar system. Chapter N. In this video we will explore the real story of 3 Atlas, without speculation or fantastic theories, only confirmed science. We will analyze how it was discovered, what makes it different from any known comet, and why astronomers from NASA and ESA are so interested in it. Before we analyze the non-gravitational acceleration of 3I Atlas and what it reveals about its internal structure, there are 3 crucial actions you need to take to join this global investigation. First, give this video a like. This is not just a gesture. It helps scientific algorithms and outreach platforms prioritize this discovery, pushing this crucial data to more researchers and amateur astronomers worldwide. Second, subscribe and turn on the notification bell. The observation window for this interstellar visitor is limited, and we will be publishing real-time updates from the Very Large Telescope and the James Webb Space Telescope as they come in. And third, this is critical. Go down to the comments section and type the word interstellar. Your comment will register your participation in this global tracking community, helping us measure the public impact of this once-in-a-generation event. Every like, subscription, and comment amplifies the reach of this discovery. Do it now and let's continue with the analysis. Throughout this investigation you will hear names like Pan-STARRS, James Webb and Vera Rubin. Each of these observatories is contributing unique data to understand what this interstellar traveler is made of. We will see how its brightness changes, how the Sun's heat releases gases from its surface, and what that can tell us about its origin. 3I Atlas is not just another comet, it is a piece of the cosmic puzzle that could show us how planetary systems beyond our own form. As it approaches the Sun, the enigma becomes more intriguing, and each observation brings us a little closer to understanding its true nature. In the early morning of February 12, 2024, a telescope at the summit of the Haleakala volcano in Hawaii recorded a point of light moving slowly among the stars of the constellation Virgo. At first glance, it seemed an ordinary comet, one more among the hundreds that the Atlas tracking system detects every year. However, preliminary calculations showed something that made astronomers stop everything. That object's orbit did not close around the Sun, it was hyperbolic. That meant it did not come from our solar system. It had crossed interstellar space to reach us. The Atlas team, an automated system designed to detect asteroids potentially hazardous to Earth, confirmed the anomaly. The tracking data obtained in just 3 nights showed a trajectory that did not match any known comet. The new visitor was provisionally named 3I Atlas, where 3I indicates it is the third interstellar object ever observed. After Oumuamua in 2017 and 2I Borisov in 2019, the designation Atlas honors the system that detected it. Unlike Oumuamua, which showed no signs of cometary activity, 3I Atlas presented from the beginning a diffuse coma, a bluish-green glow that betrayed the presence of gases released by solar radiation. This facilitated its spectroscopic study, allowing analysis of the composition of its volatile material. The first analyses revealed unusual proportions of cyanogen CN and diatomic carbon, C2, substances responsible for the intense green color often observed in some active comets. However, the detected quantities were much larger than usual, and that sparked the interest of the international astronomical community. Within days, observatories across the planet coordinated to follow the object. The Pan-STARRS telescope in Hawaii, the Lowell Observatory in Arizona, and the European Southern Observatory in Chile began recording high-resolution images. The measurements confirmed that 3I Atlas was moving at more than 95,000 km per hour relative to the Sun, a speed too high to belong to our system. The shape of its orbit indicated it would approach perihelion, its point closest to the Sun, at the end of 2025, before definitively escaping into interstellar space. Meanwhile, astronomers tried to determine where it came from. By tracing back its trajectory in simulations, they discovered it had entered the solar system from the direction of the constellation Hercules, albeit with considerable uncertainty. This implies its origin could be in some region located between the stars Vega and Deneb, in the arm of the Milky Way opposite to our own. The fact that a fragment of matter from another stellar system could reach here is in itself a reminder of how interconnected the cosmos is. But beyond its provenance, the comet's behavior began to reveal intriguing characteristics. The observations showed variations in its brightness, as if it were pulsing. This phenomenon, known as photometric variability, can be due to irregular rotation or an elongated shape that reflects light unevenly. However, the changes in 3I Atlas were more pronounced than normal, suggesting a combination of factors: chaotic rotation and intermittent release of gases from different points on its surface. The Hubble Space Telescope managed to record its coma in great detail. The analyses showed that the dust density around the nucleus was low, indicating a small body, probably less than 1 kilometer in diameter, but extremely active. This type of behavior is not common in such diminutive comets. Therefore, some researchers from the Institute of Astronomy at Harvard University suggested that 3I Atlas might have passed very close to a star in the past, which could have fractured part of its surface and left deep cracks through which gases escape upon heating. While the first scientific articles were being published, another puzzling detail emerged. The observed acceleration in its movement could not be explained by solar gravity alone. This effect, known as non-gravitational acceleration, had already been observed in Oumuamua, but in that case it was attributed to a release of gases acting like a small engine. In the case of 3I Atlas, the measured forces were greater than expected for the amount of material it was emitting. Astronomers at NASA's Jet Propulsion Laboratory began modeling different possibilities. One of them was that the gas jets came from highly localized regions and were oriented in specific directions, generating an asymmetric net impulse. Another possibility was that the comet had a composition extremely rich in volatile compounds like frozen carbon monoxide or methane, which upon sublimation would produce more powerful thrusts. In any case, the magnitude of the acceleration indicated that 3I Atlas was different from any other known object. The mystery grew with each new observation. The comet's color, its variability, and its trajectory suggested it was a very primitive body, perhaps formed in the icy outskirts of another solar system where stellar radiation barely has an influence. If this is true, 3I Atlas could be a time capsule, a fragment of the original materials that formed planets elsewhere in the galaxy. Studying it means glimpsing the remote past of worlds we will never see. By mid-2024, the European Southern Observatory's Very Large Telescope had detected faint signs of an ionic tail formed by charged particles expelled through interaction with the solar wind. This finding confirmed that the comet was actively responding to solar radiation. Scientists hope that as it gets closer to perihelion, the activity will increase and new details of its structure will become visible. At that point, 3I Atlas became a priority target for the astronomical community. Coordinated observations were scheduled with the James Webb Telescope, capable of analyzing infrared light and detecting complex organic compounds. If molecules like methanol, ammonia, or formaldehyde were found, it could be deduced that the comet comes from a region where chemical conditions were favorable for the formation of organic matter, something that would expand our understanding of how the ingredients of life are spread throughout the cosmos. The story of 3I Atlas is just beginning. Each new piece of data opens a question, and each image reveals another piece of the puzzle. Its passage through the solar system will last only a few months, but the observations obtained could serve for decades to understand how planetary systems beyond our own are born and evolve. In its silent journey, this small interstellar visitor reminds us that we are not the center of the universe, but part of a vast fabric of worlds and stars interconnected by time and space. From the first orbital calculations, scientists noticed that 3I Atlas did not follow the typical behavior of comets orbiting within the solar system. Its trajectory was not elliptical like that of comets that return periodically, but hyperbolic, which means it entered the system from interstellar space and will exit, never to return. This type of orbit is the unequivocal signature of an interstellar traveler, a body that does not belong to the Sun or any planet that surrounds it. Initial models from the Jet Propulsion Laboratory showed that the comet came from the approximate direction of the constellation Hercules. It was moving with a heliocentric velocity exceeding 100,000 km per hour, sufficient to escape the Sun's attraction. When its complete path was projected, astronomers observed that it would cross the plane of the ecliptic, where most planets orbit at a steep angle, which hindered any significant gravitational interaction with them. As the positional data were refined, surprising details emerged. 3I Atlas showed a slight lateral deviation, a curvature that did not match purely gravitational calculations. Although small, this difference was statistically significant. In interstellar objects, even a minimal variation can reveal much about their composition or the way they respond to solar radiation. To better understand its trajectory, astronomers turned to observations from the Vera Rubin Telescope, which every night records enormous amounts of data from the southern hemisphere sky. The follow-up images showed that the comet had an irregular rotation, probably caused by jets of gas being released asymmetrically from its surface. That uneven expulsion can act as a sort of thruster, altering its movement in a subtle but detectable way. However, the most disconcerting thing was the stability of these variations. If the jets came from fixed points on the comet, the direction of the impulse should change as the object rotates. But in 3I Atlas, the direction of the deviation remained constant for several weeks. This consistency suggested that the phenomenon was not just an effect of its rotation, but the result of a complex internal structure or a particularly volatile composition. The team from NASA and ESA began comparing the trajectory of 3I Atlas with that of the two previous interstellar objects. Oumuamua had shown similar anomalous movement, though without visible gas emission. In contrast, 2I Borisov behaved like a typical comet with a slightly hyperbolic orbit and a stable coma. 3I Atlas seemed to sit between both. It showed visible activity, but also an unexplained acceleration. Calculations performed at the Minor Planet Center of the International Astronomical Union indicated that its perihelion, the point closest to the Sun, would occur at a distance of approximately 0.9 astronomical units, slightly inside Earth's orbit. This relative closeness makes it an ideal object for terrestrial and space observations. Unlike Oumuamua, which was detected when it was already moving away from the Sun, 3I Atlas can be studied throughout its approach. The scientific community is preparing for this moment with a level of coordination rarely seen. Teams from observatories in Europe, America, and Asia are synchronizing their measurements to precisely record any change in its brightness, color, or speed. The objective is to build a three-dimensional model to understand how solar radiation affects a body coming from another stellar system. Preliminary analyses show that its shape could be elongated and irregular with approximate dimensions of 700 meters by 300 meters. This morphology, similar to a torn fragment, could be the result of a violent event in its system of origin, the collision between two planetesimals or the ejection of debris following the disintegration of an icy planet. If this hypothesis is correct, 3I Atlas would literally be a piece of another world. Meanwhile, the James Webb Space Telescope has begun a series of infrared observations to measure the comet's surface temperature and thermal emission. The first results indicate that the surface reflects less light than expected, suggesting a dark, carbonaceous material, similar to that found in long-period comets. This type of composition absorbs solar radiation better, which accelerates the sublimation of the ices and may explain its high activity. Despite these advances, a key question remains. Why does its acceleration not fit the standard model? Astrophysicist David Farnokia from JPL commented in a recent interview that the measured forces are too large for the amount of gas we observe. For this discrepancy to make sense, 3I Atlas would have to possess extremely active escape regions. Perhaps cracks that concentrate internal pressure until they release jets with great momentum. Another possibility is that the chemical composition of the comet is different from that of any body in the solar system. If it contains elevated proportions of frozen carbon monoxide, the gas could sublimate even at great distances from the Sun, creating a persistent acceleration. This hypothesis will be tested during its approach when the Webb and ESA's solar orbiter measure the gas emission rate. Beyond the immediate science, the study of 3I Atlas offers a unique opportunity to understand the processes that occur in other planetary systems. The way it behaves upon receiving sunlight can reveal details about the environment from which it comes, the temperature of its original star, the composition of the protoplanetary disk, and even the presence of complex organic elements. Each piece of data is a window into a place from which we have no other way of obtaining samples. The orbital behavior has also generated interest among experts in celestial dynamics. Simulations suggest that before entering our solar system, 3I Atlas may have passed near a star in the HIP catalog, HIP 54, around 700,000 years ago, receiving a gravitational impulse that altered its direction and sent it toward us. This type of wandering trajectory shows how stellar systems interact over enormous timescales, exchanging fragments of material like seeds traveling through the galaxy. As the comet advances, its velocity relative to the Sun continues to increase, driven by solar gravity. In the coming months, astronomers expect to observe drastic changes in its brightness as gases trapped beneath the surface are released. This phase will be crucial for determining the relationship between its mass, its density, and the type of materials that compose it. The closer it gets, the more information can be obtained about its interior. But scientists also know that time is limited. Once 3I Atlas passes perihelion, it will begin its definitive exit, and with each passing day it will become more difficult to observe. Therefore, the upcoming observation campaigns are vital. Every image, every spectrum may contain clues about its origin, its composition, and the mechanisms driving its mysterious acceleration. The study of its trajectory will not only help understand 3I Atlas, but also prepare humanity for future interstellar visitors. The probability that thousands of similar objects are crossing the galaxy is high, and each one could bring valuable information about the formation processes of planetary systems. 3I Atlas is, in this sense, a messenger from deep space, a fragment from another time and another sun that now is reflected in the eyes of our telescopes. During the first months of observation, astronomers' attention focused on the unusual way in which 3I Atlas reflected sunlight. Unlike typical comets, whose brightness increases predictably as they approach the sun, this object showed erratic variations in its luminosity. On some nights it became up to 3 times brighter, only to decrease abruptly afterward. Data from the Vera Rubin Observatory and Pan-STARRS showed that these fluctuations did not follow any stable pattern. It was as if the comet were breathing, expanding and contracting in irregular cycles. To understand the cause of these variations, observations from different instruments were combined. The Subaru telescope in Japan recorded changes in color intensity, suggesting that the brightness was not the product of simple reflections, but of active physical processes. The most consistent models indicated that the comet was releasing gases intermittently from deep cracks on its surface. When solar radiation heats these zones, the trapped gases expand abruptly, pushing dust particles into space. This expulsion generates a sudden increase in luminosity, followed by a decrease when the activity stabilizes. However, something in 3I Atlas did not fit the known laws. The brightness explosions were too intense for the amount of material such a small body could release. Simulations performed by the Jet Propulsion Laboratory showed that if it were only ice sublimation, the increase in light should be much smaller. The hypothesis that began to gain strength was that the comet possessed zones of very heterogeneous chemical composition, with regions rich in extremely volatile compounds, among them frozen carbon monoxide CO and methane CH4, capable of sublimating even at very low temperatures. When these gases are released, they not only increase the brightness but also modify the shape of the coma, the cloud surrounding the nucleus. Observations from the Very Large Telescope in Chile revealed that the coma of 3I Atlas was not symmetrical. It extended more to one side as if a gas jet were pushing the material in a preferred direction. This asymmetry confirmed that the comet was not rotating uniformly. Its spin was chaotic, altered by internal explosions. The Hubble Space Telescope managed to capture high-resolution images during one of these brightness peaks. Spectroscopic analyses showed unusual peaks in the emission bands of cyanogen Cn and diatomic carbon C2, responsible for the characteristic bluish-green hue of some comets. But the intensity of these spectral lines in 3I Atlas was exceptional. No known comet within the solar system had shown such high concentrations. Researchers from the Max Planck Institute for Astronomy suggested that these compounds might be more concentrated because the comet formed in a stellar environment colder and with less ultraviolet radiation than that of our Sun. This discovery aroused great curiosity. If 3I Atlas contains materials that were preserved for billions of years in interstellar space, it could offer a direct window into the chemical past of other planetary systems. Every molecule observed in its spectrum is a clue about the conditions in which it was born. Therefore, the team of the James Webb Space Telescope JWST scheduled a series of observations in the mid-infrared range with the aim of detecting the presence of complex organic molecules like formaldehyde, H2CO, ethanol, C2H5OH, and ammonia, NH3. The first results from Webb, obtained at the end of 2024, confirmed the presence of several of these compounds, albeit in small quantities. This was enough to classify 3I Atlas as one of the most interesting interstellar objects ever observed. What most caught attention was the variability of the infrared brightness, which increased and decreased in synchrony with the visible light. This pattern indicated that the luminosity explosions did not come only from solar reflection, but from real changes in the comet's thermal emission, that is, from the heat generated by the sublimation of its components. But the story of the brightness does not end there. As the object approached the sun, its color began to turn bluer, a tone scientists did not expect. In common comets, solar activity usually produces a more whitish or yellowish tone, because dust dominates the scattering of light. In 3I Atlas, in contrast, the color indicated that gases were gaining prominence. This led to the thought that the comet was losing part of its surface material, exposing a purer layer of ice and volatile compounds. The luminous behavior of 3I Atlas offered a unique opportunity to study how an interstellar object reacts upon coming into contact with solar radiation. In a certain sense, it was a natural experiment, a fragment from another stellar system subjected to the conditions of our Sun. Astronomers took advantage of every minute of observation to measure its light curve, its rotation, and the color variations. These measurements will serve as a reference for future detections of interstellar visitors. In scientific forums, comparisons with the mysterious Oumuamua began to emerge. That object also showed non-gravitational acceleration and variability in brightness that was never fully explained. However, 3I Atlas offered a crucial advantage. Its activity was visible and measurable, which allowed the application of concrete physical models. If the brightness variations coincided with the patterns of gas release, it could be demonstrated that similar phenomena also explain Oumuamua's behavior, thus closing a debate that has been going on for years. At the same time, the study of 3I Atlas's irregular brightness helped refine comet formation models. Some researchers from the European Southern Observatory proposed that interstellar objects could form in the outer regions of binary systems, where the gravitational forces of two different stars eject fragments into space. In that type of environment, bodies can acquire unusual chemical compositions with alternating layers of volatile materials and refractory rocks. This would explain why, upon heating, 3I Atlas releases gases in violent episodes. Every time the comet experienced a sudden increase in brightness, astronomers recorded an additional phenomenon, a slight alteration in its movement. These small accumulated impulses modified its trajectory by just a few meters per second, but they were enough to demonstrate that the non-gravitational acceleration was directly linked to the changes in luminosity. The brightness, therefore, was not just a visual spectacle, but a physical manifestation of the comet's internal power. On the clearest nights, amateur observatories in Mexico, Chile, and Spain managed to capture images of the green coma. Although to the naked eye it was only seen as a faint spot, long-exposure photographs showed a fascinating structure, with filaments of gas extending in opposite directions. These images, shared by amateur astronomers on scientific platforms, helped build a global record of the comet's behavior, complementing the professional data. The changing brightness of 3I Atlas has become one of the keys to understanding its nature. Every luminous pulse is a signal of what is happening beneath its surface: chemical reactions, fractures, gas release, and the direct interaction with the radiation of our Sun. It is possible that upon reaching its perihelion, the comet will become even brighter, allowing observation of its nucleus with unprecedented precision. If that happens, we could discover not only what it is made of, but also how matter that travels between the stars behaves. The mystery continues to grow, but now the comet's light offers us something more than beauty. It is showing us the invisible mechanisms that govern the life and death of celestial bodies. Every flash on its surface is a message from a distant system, a reminder that the chemistry and physics of the universe are the same everywhere, although they manifest in forms we do not yet fully understand. The color change in 3I Atlas was what finally cemented its reputation as one of the most enigmatic objects ever observed. At first, the comet showed a greenish tone typical of the presence of cyanogen and diatomic carbon in its coma. But as it approached the Sun, that tone became brighter and acquired a bluish radiance that no other comet had shown with such intensity. The cameras of the Very Large Telescope and Subaru recorded this spectral shift with great precision, and astronomers realized they were facing a unique chemical phenomenon. The green color of comets is usually the product of the decomposition of cyanogen Cn and diatomic carbon C2 when ultraviolet light from the Sun breaks the molecules. This luminescence appears only in the coma, not in the tail because the gases dissociate before getting too far from the nucleus. In 3I Atlas, however, the emissions from Cn and C2 were accompanied by an unusually high contribution of ionized carbon monoxide, CO+, which glows with a blue tone. This detail, confirmed by spectra from the James Webb Space Telescope, indicated a proportion of gases very different from that of any comet in the solar system. The team from the Institute of Planetary Sciences analyzed the spectra and concluded that 3I Atlas must contain deep layers of carbon monoxide and carbon dioxide ice, kept stable for millions of years in the cold of interstellar space. As it approached the Sun, these ices began to sublimate, generating a mixture of green and blue emissions. This chromatic combination, brighter than in any other observed comet, became a chemical fingerprint of its origin. The phenomenon also revealed information about the object's internal structure. Common comets are composed of a relatively homogeneous mixture of ices and dust. In 3I Atlas, the observations suggest that the most reactive volatiles are concentrated in specific regions, probably beneath a surface layer of darker material. When solar heat penetrates deeply enough, these pockets open violently and release jets of gas that ionize the surroundings. The visible result is a sudden expansion of bluish-green color that can last for hours or days before fading. To study this behavior, the European Southern Observatory initiated a series of daily monitoring sessions. It was discovered that the color outbursts coincided with temporary increases in the gas expulsion velocity. That is to say, the change in tone was not just an optical effect. It corresponded to a real physical variation in the composition of the coma. Every time the blue tone predominated, the spectrum showed an increase in the proportion of CO+ and a reduction of Cn. This indicated that different zones of the nucleus were activating successively, releasing different gases depending on the depth of the heating. Researchers from the Center for Astrobiology in Madrid proposed that this alternation of colors could be a marker of the object's thermal history. If 3I Atlas formed in a colder stellar system, its internal layers would have accumulated substances that cannot survive in the solar environment. The fact that these molecules still exist suggests the comet was never exposed to high temperatures before entering our system. If confirmed, this would be direct evidence that interstellar ices can remain intact for cosmic timescales. Beyond the background, the bluish-green color also sparked the interest of astrophysicists studying the chemistry of cometary plasma. In the spectra obtained by the Webb telescope, emission lines corresponding to excited ions of carbon and oxygen were detected, formed when solar wind particles collide with the comet's gases. This interaction produces a bluish luminescence known as ionization fluorescence, a phenomenon rarely observable with such clarity. In 3I Atlas, the intensity of these lines was more than double that recorded in comets from our system. This suggests the material released by the object is more susceptible to ionization, perhaps due to an unusual proportion of light gases. Simulations performed at NASA's Goddard Center showed that as the comet approaches the Sun, the interplanetary magnetic field can guide the ionized particles from its tail, creating filaments that vary in color between green and blue. Indeed, in several Hubble images, spiral structures are observed changing tone from one day to the next. These variations are visual evidence of how the solar wind shapes the comet's tail and simultaneously allow us to study the properties of the solar plasma. Meanwhile, astronomers from the National Autonomous University of Mexico compared the spectrum of 3I Atlas with those of other comets recorded in recent decades. Their analysis showed that the ratio of Cn to CO+ of the interstellar object does not resemble that of any comet from the Oort cloud or the Kuiper belt. It is a completely new type of icy body, which implies that planetary systems can produce chemical compositions far more diverse than previously thought. The comet's chromatic behavior may also help resolve an old enigma in astrophysics. How are light elements distributed throughout the galaxy? Every time an interstellar comet passes near a star, it releases part of its material into the interstellar medium. If these objects are common, they could contribute significantly to enriching the galactic gas with carbon, oxygen, and nitrogen, the fundamental ingredients for life. Thus, 3I Atlas is not only a distant visitor but also a chemical messenger carrying the imprints of its system of origin. The color change was so notable that even amateur observers were able to record it. In Mexico, the telescopes of the National Astronomical Observatory in Tonantzintla managed to photograph the transition from green to blue over an interval of just 1 week. The images disseminated in specialized publications showed how the comet's coma acquired a luminous turquoise tone against the starry background. This phenomenon captured the attention of the scientific press and generated an increase in the number of observers interested in following its evolution. Scientists from the European Space Agency's Solar Orbiter also seized the opportunity to measure how solar radiation interacts with the comet's material. Preliminary data indicated an increase in electron density in the surrounding region, direct evidence that 3I Atlas was injecting plasma into the solar wind. This process, although local, allows the study of how comets can temporarily alter the electromagnetic environment of the heliosphere. The bluish-green color of 3I Atlas has thus become a scientific tool more than a mere visual curiosity. Analyzing its spectrum allows for the determination of the proportion of volatile compounds, the ionization speed, and the structure of the solar magnetic field in the region where it travels. It is an extraordinary coincidence. While scientists seek to understand what the comet is made of, the comet itself is offering them data about the Sun. As the distance to the star decreases, models predict that the blue emissions will completely dominate the coma. If this is confirmed, it will mean that carbon monoxide and carbon dioxide are the main components of its surface. This finding would have profound implications. It would confirm that the protoplanetary disks of other stars can form bodies with compositions radically different from those in our own. In other words, 3I Atlas would be a tangible sample of the chemical diversity of the universe. Astronomers know the chromatic spectacle will not last long. As the comet gets closer to the Sun, the intensity of the radiation could fragment part of its nucleus. In that case, the blue color would fade and the dust cloud would become whiter, typical of comets in the process of disintegration. Therefore, the scientific community is taking advantage of every day of observation before the object reaches its perihelion. Every blue photon captured by a detector represents information that may never be repeated. The study of the color of 3I Atlas demonstrates how light, when broken down into its components, can tell a story of origin and transformation. In its bluish-green glow is written the chemical history of another solar system, the memory of a place where matter formed under different conditions. As it continues its journey toward the Sun, that radiance becomes a visible reminder that the materials composing worlds, carbon, oxygen, hydrogen, are universal, shared by all stars and planets in the galaxy. When the first complete spectra of 3I Atlas reached the scientists, the surprise was immediate. Its composition did not match that of any comet in the solar system. Most known comets contain a mixture of water ices, carbon dioxide, carbon monoxide, and small amounts of silicates and metals. But the spectra of 3I Atlas showed something radically different. An enormous abundance of light compounds and an almost total absence of metallic materials. It was as if it had been born in an environment where heavy elements never managed to condense. Astronomers from the Max Planck Institute compared their data with that of 2I Borisov, another interstellar visitor. Borisov had a composition similar to that of common comets, rich in water, dust, and some iron. 3I Atlas, in contrast, presented elevated proportions of methane, ammonia, and carbon monoxide, but a scarcity of silicates and metals. This difference suggests it formed in an extremely cold region, possibly beyond the snow line of its system of origin, where metals remain in a gaseous state and fail to incorporate into cometary nuclei. Scientists at NASA's Goddard Space Flight Center modeled the temperatures necessary for such an object to form. Their calculations showed that the observed mixture could only remain stable at temperatures below 253 Kelvin, conditions typical of the outer edges of stellar systems or even of interstellar space between molecular clouds. In other words, 3I Atlas could originate from a zone where the light from its star barely managed to heat the primordial dust. The James Webb Space Telescope, thanks to its infrared spectrograph, detected a clear signature of complex organic molecules. Traces of methanol CH3OH, formaldehyde H2CO, and ethanol C2H5OH were identified, substances that on Earth are associated with prebiotic processes. Although there are no biological implications in this context, their presence confirms that organic chemistry is universal and develops in different stellar environments. The detection was received with enthusiasm because it implied that the basic ingredients of life can form even outside our cosmic neighborhood. Another puzzling discovery was the comet's low density. Through observations of the coma's motion and the velocity of the gas jets, researchers estimated an average density of less than 0.3 grams per cubic centimeter, much lower than that of traditional comets. This means that 3I Atlas is extremely porous, perhaps a fragile structure formed of loose particles weakly bound by ice. Such a light composition implies it could fragment easily as it approaches the Sun, something astronomers are closely monitoring as the object nears its perihelion. Detailed analysis of the ejected dust also yielded unexpected results. The particles were unusually small, sizes less than 1 micron, and their composition indicated the presence of amorphous carbon and ultrafine silicates. The lack of metallic grains was confirmed by spectra in the mid-infrared range, where the signatures of iron and nickel are normally detected. In 3I Atlas, those lines were absent. This fact reinforced the idea that the comet formed in a chemically different environment from our own, where heavy elements remained gaseous or were expelled before condensing. Some researchers from the University of Cambridge proposed a more ambitious hypothesis, that 3I Atlas could originate from a binary system where one of the stars was a red dwarf. In those environments, extreme temperatures and strong stellar winds can eject material into interstellar space. If the comet was ejected from there, it would explain its unusual composition and low density. It would be a fragment formed in the outer regions of a protoplanetary disk orbiting two suns. A fascinating scenario that until now had only been simulated on computers. The team from the European Southern Observatory also studied the relationship between gas emission and brightness variability. They discovered that the release of carbon-rich gases coincided with increases in reflected ultraviolet radiation. This implies that the comet's surface is extremely active and responds almost instantaneously to changes in solar temperature. Within hours it can transition from an inert state to one of intense activity, as if its interior were breathing with the sun's heat. Meanwhile, the ESA coordinated observations with the Solar Orbiter satellite to measure how solar wind particles interact with the comet's gases. The instruments detected fluctuations in the plasma density around 3I Atlas, which suggests its composition has a direct effect on the dynamics of the interplanetary environment. These measurements help understand how comets can influence, albeit subtly, the flow of the solar wind and the local magnetic structure. One of the most relevant findings came from the isotopic analysis of the gases. The ratios of carbon-12 to carbon-13 and of nitrogen-14 to nitrogen-15 were different from those of any comet in the solar system. This means that 3I Atlas formed from a molecular cloud with a different isotopic signature, offering direct evidence that stellar systems are born in chemically diverse regions of the galaxy. In simple terms, the comet carries the fingerprint of its parent star. Scientists also focused on the role of water. Unlike comets from the Oort cloud, 3I Atlas seems to have a surprisingly low proportion of water. The spectra show weak lines of water vapor, suggesting this component is not dominant. This poses an enigma. How could a comet form with almost no water in a cold environment? One possible explanation is that water never managed to condense in its region of origin, perhaps because the levels of ultraviolet radiation or the density of the disk were different from those in our system. Researchers from the Harvard-Smithsonian Center for Astrophysics argue that the absence of water and the abundance of methane point to a formation scenario outside the boundaries of the main protoplanetary disk, in a zone where carbon compounds predominated. If this model is correct, 3I Atlas would be the first direct sample of a type of body that until now only existed in theory, pure carbon comets, icy fragments composed mainly of volatile organic compounds. Every new piece of data about its composition redefines what astronomers believed was possible. Before the arrival of interstellar objects, it was thought that all planetary systems produced icy bodies with more or less similar characteristics. But 3I Atlas is demonstrating that the chemical diversity of the cosmos is far greater than imagined. Instead of being an exception, it could represent a completely new category of galactic visitors. As it approaches the Sun, the chemical differences of 3I Atlas become more evident. Telescopes continue to detect an increase in the emissions of CO and CH4, while the signals for water remain weak. This evolution confirms that the ices dominating its surface are more volatile than water, which explains its intense activity at temperatures where other comets remain dormant. In the coming months, scientists expect this combination of materials to generate visible phenomena like irregular jets and extreme variations in its brightness. The composition of 3I Atlas not only challenges known cometary categories, it also puts planetary formation models to the test. Every molecule detected, every isotopic ratio measured, expands our understanding of how matter groups together and evolves in different corners of the galaxy. In essence, the comet is acting as an interstellar messenger, bringing within its interior the chemical memory of a solar system we will never see, but which we now know a little better thanks to its fleeting passage through our cosmic neighborhood. When researchers examined the spectra of 3I Atlas in greater detail, they encountered an unexpected void. The absorption and emission lines that usually indicate the presence of iron, nickel, and other heavy metals simply did not appear. In common comets, those spectral signatures are unmistakable. They arise when metallic grains heat up and release ionized atoms that interact with sunlight. But in the case of 3I Atlas, the most sensitive instruments, the James Webb's NR-SPEC spectrograph, the VLT's UVS and Keck's Hires, did not detect any of those signals. The conclusion was resounding. The comet contained no detectable metals in significant quantities. This contradicted expectations because even the most primitive comets in the solar system, formed 4.5 billion years ago, retained traces of metals in their nuclei. The finding opened a new debate among astrophysicists. How can a body without iron exist in a universe where this element is one of the most abundant produced by supernovae? One of the first hypotheses came from the Institute of Planetology in Paris. Researchers proposed that 3I Atlas could have formed in a low-metallicity stellar system, that is, an environment where previous generations of stars had not yet enriched the medium with heavy metals. Young stars born in metal-poor regions produce protoplanetary disks with fewer refractory materials. In those places, icy bodies are composed almost exclusively of light compounds like methane, carbon monoxide, and nitrogen. If 3I Atlas comes from such a system, it would be a relic from the early times of the galaxy. Another possibility, defended by the team at the Harvard Center for Astrophysics, is that the comet did originally contain metals, but lost them during its interstellar traverse. Over millions of years of exposure to cosmic radiation and micro-impact bombardment, the metallic particles could have been eroded or expelled, leaving only the more volatile components. This process, known as interstellar outgassing, would have transformed an originally mixed body into a nucleus dominated by light compounds. To test these ideas, the observations of 3I Atlas were compared with those of 2I Borisov. Borisov did show iron and nickel, meaning that not all interstellar objects lack metals. Therefore, 3I Atlas seems to represent a different class, an object that formed in a chemically primitive environment or that underwent an extreme purification process. In both cases, its existence provides a clue about the chemical diversity of stellar systems. The analysis of the absence of iron also had dynamic implications. Comets with metallic content usually have higher density and higher thermal inertia, which regulates their activity when they approach the Sun. In contrast, 3I Atlas, lacking metals, has very low thermal conductivity, meaning its surface heats up rapidly while the interior remains frozen. This difference causes internal stresses that can lead to fractures and localized explosions. Indeed, the sudden increases in brightness observed in previous weeks could be due to these outbursts provoked by the uneven heating of the nucleus. The James Webb detected variations in the infrared emission that support this hypothesis. During peaks of activity, the surface temperature increased to around 190 Kelvin, while the interior remained at less than 180 Kelvin. That extreme thermal difference generates pressures that break the comet's crust, allowing the accumulated gases to escape at high speed. Without the structural reinforcement of metallic minerals, 3I Atlas behaves like a fragile conglomerate, a kind of cosmic sponge held together by ice. Astronomers from the Institute of Planetary Sciences also noted that the lack of metals directly affects the comet's interaction with solar radiation. Metals act as thermal and electrical regulators. They reflect part of the energy and contribute to forming local magnetic fields in the coma. Without them, the comet's material is more vulnerable to the solar wind, which explains why the ionic tail of 3I Atlas is so extensive and reactive. The radiation penetrates more deeply into the material, producing more intense ionization than in conventional comets. This metallic deficiency, far from being a flaw, turns 3I Atlas into a natural laboratory for studying the physics of comets in extreme environments. Models developed by the ESA show that during its approach to perihelion, the comet could release large quantities of ionized gas, creating a small induced magnetic field around its nucleus. Observing this phenomenon would allow an understanding of how bodies without metals interact with solar plasma, something that had never been directly measured before. Scientists from the Geneva Observatory seized the opportunity to investigate the evolution of iron in the galaxy. If 3I Atlas originates from a region with extremely low metallicity, it could offer a clue about the processes of star formation in the primitive Milky Way. Its composition suggests that zones where iron and nickel are scarce still exist, vestiges of an era prior to the proliferation of supernovae that seeded the galaxy with heavy elements. In addition to metals, a notable deficiency in silicates was detected. The dust particles collected by infrared spectra lack the characteristic signature of the minerals olivine and pyroxene, common in local comets. Instead, the dust of 3I Atlas seems to be composed of amorphous carbon and refractory organic compounds. This finding reinforces the idea that the comet originates from an oxygen-poor environment, where carbon dominated the chemistry of the protoplanetary disk. The study of iron, or rather its absence, has also served to question the boundary between interstellar comets and asteroids. If 3I Atlas lacks metals and rocky minerals, its structure is radically different from that of an asteroid. This suggests that interstellar objects do not belong to a single category, but form a continuous spectrum of compositions, from silicon-rich bodies to fragments dominated by ice and carbon. Some astrophysicists see in this finding a broader learning opportunity. Understanding how and where objects without metals can form offers clues about the first steps of cosmic chemistry at the dawn of the galaxy. Before supernovae scattered heavy elements, solid bodies must have been composed almost exclusively of simple molecules. If 3I Atlas comes from such a place, it would be carrying within its interior an intact sample of the most primitive matter in the universe. The coming months will be decisive. As the comet gets closer to the Sun, the increase in temperature could reveal whether traces of metallic minerals remain hidden beneath its surface layer. If none are detected, scientists will be able to confirm that we are facing an object formed in an almost metal-free environment. Otherwise, its composition will offer a unique view of the degradation process that bodies undergo during their interstellar travel. Whatever the outcome, the absence of iron in 3I Atlas has already redefined the boundaries of astronomical knowledge. Its study demonstrates that matter traveling between the stars can be far more varied than we ever imagined. By observing it, we are not just seeing a comet, we are contemplating a fragment of the galaxy's chemical history, a living sample of how the universe evolves from the simplest elements toward the complexity that makes life possible. As 3I Atlas advances toward the inner solar system, the Sun becomes the dominant factor in its evolution. Solar radiation, composed not only of visible light but also ultraviolet rays and a flux of charged particles, begins to transform the comet in an irreversible way. Every degree that its surface temperature increases provokes a series of physical and chemical reactions that release gases, dust, and plasma into space. For scientists, this process is a unique opportunity to observe how an interstellar object responds to an energy source completely distinct from that of its system of origin. Telescopes and space probes have documented this change with unprecedented precision. In the first records, the comet barely showed a diffuse coma. However, as the distance to the Sun decreased below 1.5 astronomical units, that coma expanded rapidly. The ESA's solar orbiter and the SOHO spacecraft detected a sudden rise in the quantity of emitted particles. The gas flow multiplied by 10 in a matter of days. This increase was accompanied by a change in the infrared spectrum showing a clear increase in the sublimation of carbon monoxide CO and methane CH4. Thermal models developed by the Institute of Planetary Sciences demonstrated that the comet's gases are released in successive layers. First, the surface layer rich in volatile compounds activates. Then the heat slowly penetrates inward, awakening regions that have remained frozen for millions of years. This staggered process generates irregular and at times violent activity. Observers recorded several brief outbursts in which the comet's luminosity increased almost twofold. These events were interpreted as sudden releases of trapped gas under pressure. The James Webb Space Telescope captured during one of these outbursts a singular phenomenon, an intense infrared emission in the 4.6 micrometer band, a characteristic signal of the presence of carbon dioxide. This confirms that the Sun is heating increasingly deeper regions, provoking the sublimation of materials that in other comets only activate much closer to perihelion. In 3I Atlas, the response to solar radiation is faster and more energetic, which reinforces the idea that its surface is extremely porous and sensitive. But the Sun's influence is not limited to heating. The solar wind, a constant flow of protons and electrons emitted by the solar corona, interacts with the comet's atmosphere and creates a region known as the ionic coma. In the case of 3I Atlas, this interaction is particularly intense due to the absence of metals in its composition. The charged particles of the solar wind penetrate more easily into the comet's gas, generating ionization and producing a luminous blue tail that extends millions of kilometers behind the nucleus. The solar orbiter's magnetometer recorded local variations in the magnetic field near the comet's estimated position, which suggests that the ionic tail of 3I Atlas interacts directly with the magnetic structure of the solar wind. These observations are valuable because they allow for the first time the measurement of how an interstellar body temporarily modifies the electromagnetic environment of the inner solar system. Scientists call this transient magnetic coupling, a phenomenon that until now had only been modeled in computer simulations. The increase in radiation also provokes chemical transformations on the comet's surface. Dust grains coated with hydrocarbons begin to carbonize, which darkens some regions of the nucleus. At the same time, ultraviolet light breaks molecular bonds and generates free radicals that recombine into new complex organic molecules. In the laboratory, similar processes are used to simulate prebiotic chemistry in space. Observing it directly in 3I Atlas offers real confirmation that solar radiation can induce chemical synthesis even at millions of kilometers of distance. Astronomers are also attentive to the possible non-gravitational forces produced by the comet's activity. Every jet of escaping gas generates a small impulse, altering its trajectory in an almost imperceptible but cumulative manner. At first, these deviations are minor, a few meters per second, but over time they can modify its observable orbit. The team at the Jet Propulsion Laboratory detected that after several outbursts the mean acceleration of 3I Atlas had changed slightly, enough to adjust the predictions of its passage through perihelion. One characteristic that has aroused particular interest is the comet's thermal asymmetry. Observations of polarized light reveal that one of its hemispheres heats up much faster than the other, probably due to the inclination of its rotation axis. This imbalance could explain the more intense gas outbursts, since certain regions receive more solar energy during rotation. Understanding this dynamic helps scientists build more realistic models of how orientation and shape affect the evolution of interstellar comets. As the comet approaches its predicted perihelion at the end of 2025, researchers anticipate that activity will reach its peak. Some models predict that part of the nucleus could fragment due to internal stresses. This scenario would not be a catastrophe, but an exceptional opportunity to study the object's internal structure. If the comet splits, the observations will allow measurement of the density and composition of its inner layers, something that is normally impossible with intact comets. Solar radiation also affects the visual appearance of 3I Atlas for observers on Earth. Optical telescopes have noted a gradual increase in the extent of its dust tail, now visible in long-exposure photographs as a bright trail arching toward the celestial north. Observation programs in Mexico, Chile, and Spain are collaborating to track this growth, using specialized filters that separate the contributions of gas and dust. These international campaigns reflect the global interest the comet has sparked, having become the most distant natural laboratory observable from Earth. The Sun, in its role as a catalyst, is revealing the true nature of 3I Atlas. Every photon that strikes its surface triggers a physical process that releases secrets accumulated over millions of years. The interaction between the two, a mature star and an interstellar traveler, symbolizes the permanent dialogue between the stellar systems that compose our galaxy. In a way, studying how the Sun transforms this comet is also a way of observing how the energy of stars shapes cosmic material over time. Over the coming months, observations will continue intensively. The priority for scientific teams will be to document every change in its luminosity, color, and composition as the comet approaches its point closest to the Sun. In that instant, 3I Atlas could show us its most intimate structure, reveal whether its nucleus resists or fragments, and confirm how universal the processes governing the evolution of icy bodies are. What was until recently just a distant point has become a privileged witness to how the light of a star can rewrite the history of an interstellar traveler. When astronomers began to analyze the orbit of 3I Atlas with precision, they discovered something that did not fit the known laws of celestial mechanics. Data collected by the Jet Propulsion Laboratory and the Minor Planet Center showed small variations in its trajectory, fluctuations that could not be explained solely by the gravitational attraction of the Sun or the planets. These deviations, although minuscule, were consistent. The comet seemed to accelerate or change its orientation slightly without apparent cause. In the language of astrodynamics, this phenomenon is known as non-gravitational acceleration. It usually occurs when a comet releases gas unevenly, generating an impulse similar to a small engine. However, in the case of 3I Atlas, the measured magnitudes were too high compared to the amount of material telescopes observed leaving its surface. The impulse was real, but it did not correspond to the visible energy. Researchers from the Institute of Astronomy at the University of Maryland applied a thermophysical model to try to explain the discrepancy. In it, the gas jets emerging from cracks produce forces that depend on their temperature, direction, and duration. But even introducing extreme values, the results did not match the observations. This led to the thought that the comet might have active internal zones not visible, perhaps subterranean cavities connected by channels that release gas intermittently and in a channeled manner. These internal chambers would act as natural thrusters, propelling the object without the jet being directly visible. The James Webb Space Telescope confirmed that the nucleus of 3I Atlas has an unusual rotation. The changes in reflected light indicate the comet spins irregularly, probably in a motion known as tumbling or chaotic rotation. This type of spin can generate nonlinear impulses. As the body rotates unpredictably, the gas jets can point in different directions and produce accelerations that vary with each turn. This behavior complicates orbital calculations enormously. Compared to the famous Oumuamua, which also showed non-gravitational acceleration without emitting visible gas, 3I Atlas represents a golden opportunity to understand that type of anomaly with direct observations. In the case of Oumuamua, scientists had to resort to theoretical hypotheses like the invisible outgassing of molecular hydrogen. But here the process can be studied in plain sight. The ESA and NASA are collaborating to build a joint model that combines optical, spectroscopic, and thermal observations, in order to determine if the variations in the movement of 3I Atlas follow repetitive or random patterns. The first numerical simulations suggest the comet could experience a precession of its rotation axis caused by the uneven release of material. This would alter the direction of the jets, continuously modifying the object's orientation. With each rotation, the comet would receive an impulse in a different direction, accumulating subtle changes in its orbit. Over weeks, these variations become measurable from Earth. Another clue came from data from the Vera Rubin Observatory, which showed a slight shift in the time of maximum brightness relative to its theoretical orbital position. This temporal difference indicates that the gas explosions do not always occur at the point closest to the Sun, but are advanced or delayed depending on the comet's shape and how heat propagates through its surface. This thermal asymmetry creates delayed thrusts that can accumulate and modify its trajectory. Astrophysicists have developed a term to describe this type of behavior: spontaneous cometary propulsion. It is not a mysterious force, but the natural consequence of a complex geometry and composition. In a comet like 3I Atlas, with a surface full of cavities, fractures, and volatile compounds of different types, each sublimation event acts like a small chemical engine that changes its direction. Detailed analysis of radar data further showed that the comet's mass might be lower than estimated. If its density is extremely low, as previous models suggest, then a relatively small amount of gas would suffice to produce appreciable accelerations. This combination of low density and high activity would make 3I Atlas a body especially sensitive to perturbations. Astronomers from the Center for Celestial Dynamics at the University of Padua conducted exhaustive tracking using observations from different points on the planet. With these, they managed to determine that the average acceleration of 3I Atlas is on the order of 1 × 10⁻⁶ meters per second squared, about 10 times greater than that of traditional comets in the same region of the solar system. Although that figure seems insignificant, its cumulative effect over months can alter the orbit by hundreds of kilometers. What makes this finding fascinating is that the acceleration pattern is not constant. There are periods of stability followed by phases of sudden impulse. This reinforces the hypothesis that the comet has a heterogeneous and pulsating behavior, probably influenced by uneven exposure to the Sun and its complex rotation. Some scientists compare this movement to that of an unstable gyroscope whose axis continuously changes orientation. Amid these measurements, the scientific debate intensified. Some experts maintain that the variations are completely explainable by known physics, while others believe the case of 3I Atlas could force a revision of certain assumptions about the thermodynamics of interstellar comets. In any case, no one doubts that the observations are real and verifiable. The measured displacements are consistent among independent observatories, and their magnitude is sufficiently large to rule out instrumental error. As it approaches perihelion, the expectation increases. If the non-gravitational acceleration continues to increase, it could modify the comet's exit trajectory, altering the angle at which it will leave the solar system. This represents no danger to Earth. But it is a unique scientific opportunity. Astronomers will be able to compare the predicted orbit with the observed one and evaluate to what extent internal forces can alter the destiny of an interstellar body. The case of 3I Atlas also has broader implications. In recent years, scientists have detected that comets in the solar system show more complex behaviors than previously thought, with chaotic rotations, fragmentations, and asymmetric jets. But never before has it been possible to study an interstellar object in such detail. What is learned from it will serve to interpret the future detections of similar bodies that next-generation observatories, like the Vera Rubin, will find with greater frequency. At heart, What most intrigues astronomers is not the magnitude of the acceleration, but its constancy and coherence. Every deviation of 3I Atlas is like a footprint, a physical signature that reflects the relationship between its internal structure and the solar energy that envelopes it. Understanding that dance between light, gas, and movement is essential to decipher how interstellar objects respond to new stellar conditions after wandering for millions of years in the darkness of space. The inexplicable movement of 3I Atlas, far from being an unsolvable mystery, has become the starting point for a new era of study. In it converged the physics of plasma, the thermodynamics of ices, and orbital mechanics. Every deviation, every impulse, every change in its orientation offers a lesson about the diversity of worlds born beyond our sun. And although its passage through the solar system will be brief, its scientific legacy will endure long after it disappears into the darkness, heading once again into the interstellar void. As 3I Atlas approached its point of maximum brightness, the astronomical community intensified its vigilance. Observatories across the planet, from Chile to Hawaii, from the Canary Islands to Mexico, coordinated so as not to miss a single second of the scientific spectacle this interstellar visitor offered. Every night, optical telescopes and radio telescopes pointed toward its position, capturing thousands of images and spectra. It was the first time humanity observed with such precision a comet coming from another stellar system, and the amount of information gathered began to challenge the analysis capacity of the teams. The James Webb Space Telescope became the most valuable tool. Its sensitivity to infrared allowed it to see through the dust surrounding the nucleus, revealing hot regions that changed over time. The images showed zones of concentrated emission, as if the comet had active vents that opened and closed as it rotated. In some of them, an intermittent brightness associated with the sublimation of carbon-rich compounds was detected. Each of these observations was confirmed by the Vera Rubin Observatory, allowing the construction of a three-dimensional map of the comet with unprecedented resolution. Meanwhile, the ESA used the solar orbiter to measure how the ejection of gas and dust from 3I Atlas affected the solar wind environment. The instruments detected a temporary increase in the density of charged particles around its trajectory, which confirmed the comet was actively interacting with the sun's plasma. This type of measurement had never been achieved before with an interstellar object. Scientists observed how the solar wind deformed around the comet, creating a small magnetic bubble that moved with it. Data from pan-stars in Hawaii revealed another intriguing phenomenon. Upon analyzing the dust tail of 3I Atlas, astronomers detected a double structure. A main tail oriented in the direction opposite the sun and a second, weaker, and elongated one that seemed to extend in a slightly different direction. This type of formation, known as an anti-tail, appears when the finest particles are pushed forward by the pressure of solar radiation. However, the intensity of the anti-tail in 3I Atlas exceeded expectations. Simulations demonstrated that this pattern could only be explained if the comet was emitting ultra-fast, almost nanometric particles, something uncommon even among the most active comets. The evolution of its color also continued to be monitored. The Very Large Telescope in Subaru recorded that as the distance to the sun decreased, the bluish-green tone intensified even more, confirming the release of carbon monoxide and other ionized gases. The spectrum showed notable peaks in the lines of CO+ and Cn and a slight presence of ammonia, indicating the nucleus continues to expose increasingly deep and volatile layers. Experts from the Institute of Astrophysics of the Canary Islands suggested the nucleus could be composed of at least 3 different types of ice distributed in irregular zones that activate at different temperatures. At the same time, radiofrequency observatories began to detect weak signals and frequencies associated with hydroxyl OH, a common byproduct of the decomposition of water. Although the quantities were small, their detection confirmed that despite the low proportion of water in the comet, isolated pockets of H2O ice still exist in the interior. This discovery is important because it allows the comparison of the oxygen isotope ratio between the comet's water and that of the solar system, a key to tracing the object's interstellar origin. One of the most exciting moments occurred when the Hubble Space Telescope captured a sudden increase in the total luminosity of 3I Atlas. Within hours, the comet became almost twice as bright. The images revealed the expulsion of a visible fragment about 50 meters in diameter that slowly separated from the main nucleus. This fragment seemed to follow a parallel trajectory and showed its own mini-coma. Although it was not a catastrophic explosion, it was the first direct evidence that the comet was beginning to fragment under the sun's influence. The fragmentation of comets is not rare, but in the case of 3I Atlas it has exceptional scientific value. It allows observation of how the internal material of an interstellar body behaves when exposed for the first time to such intense radiation. Spectra taken immediately after the fragment separation showed an increase in the lines of carbon monoxide and cyanogen, a sign that the new surface was releasing more volatile gases than those detected previously. This suggests the comet's interior still preserves extremely pure ices, protected from space for millions of years. The discovery unleashed a wave of enthusiasm. Institutions like the Harvard-Smithsonian Center for Astrophysics and the Jet Propulsion Laboratory organized emergency meetings to coordinate simultaneous observations. Within less than 48 hours, more than 20 telescopes in both hemispheres were activated. Each team measured a different range of the electromagnetic spectrum, from ultraviolet to radio waves. The objective was to create a global database that would allow tracking of the fragmentation process and analyzing how the gas emissions evolve in real time. Preliminary results showed the fragment was moving away at a velocity of about 3 meters per second, a gentle separation with no signs of collision or violent rupture. Researchers concluded the event was due to internal pressures accumulated from the temperature increase and not an impact or explosion. In simple terms, the Sun had acted as a cosmic magnifying glass, heating the nucleus until a part broke off. Analysis of the tail after the event revealed notable changes in the distribution of dust. New, finer particles began to dominate the reflection of sunlight, modifying the comet's appearance in optical images. Some astronomers described the phenomenon as a rejuvenated explosion of activity, comparable to what happens when a volcano opens a new fissure. The James Webb observed that temperatures on the surface increased briefly before stabilizing, which supports the hypothesis of a localized outburst. In parallel, NASA scientists used data from the Deep Space Network to precisely measure the comet's position after the detachment. The calculations demonstrated that the release of the fragment had slightly altered its acceleration, but not enough to change its overall trajectory. 3I Atlas continued on its way to perihelion, increasingly active and bright. Astronomers also took advantage of this moment to compare the current observations with theoretical predictions made a year earlier. The coincidence between both sets of data was surprising. Almost all thermal models had anticipated an increase in activity near this distance to the Sun. This level of precision validated the simulations used and confirmed that the comet's variations, although impressive, obey well-understood physical processes. Even so, recent images continue to offer surprises. The bluish-green color of the comet has intensified to levels that make it unique among observed objects. Astronomers speculate that if the trend continues, 3I Atlas could reach a visible magnitude, even with modest telescopes in the coming weeks. For amateur observers, it would be a historic event, the possibility of contemplating with their own eyes an interstellar comet shining with a tone no other body has shown before. In astrophysics laboratories, the data keep arriving. Every spectrum, every image, every brightness measurement contributes to a puzzle that is just beginning to be assembled. Researchers agree that the study of 3I Atlas will transform the way we understand the materials wandering between the stars. This comet, which at first seemed a simple astronomical curiosity, has become a direct window into the chemistry and physics of other solar systems. As it approaches perihelion, the anticipation grows. No one knows if the comet will survive its closest encounter with the Sun or if it will end up fragmenting completely. The only certainty is that whatever happens, the observations obtained during this period will represent one of the most important scientific achievements of the decade. 3I Atlas has ceased to be just a point of light in the sky. Now it is a living witness to the exchange of matter between stars and proof that the universe is full of travelers silently crossing the boundaries between worlds. In recent decades, astronomy has revealed thousands of exoplanets, distant galaxies, and extreme phenomena. But very few events have sparked as much interest as the arrival of an interstellar object. 3I Atlas has not only expanded our knowledge about comets, it has rewritten what we understand by interstellar matter. Its passage through the solar system has been an unrepeatable opportunity to observe up close a fragment formed in an environment completely distinct from our own, a piece of another solar system that traveled for millions of years until it crossed paths with our star. The comet has taught us that the chemical diversity of the universe is far greater than we imagined. The absence of metals, the abundance of carbon monoxide, the bluish-green color, the low density, and the fragile structure are all characteristics that break the rules established by cometary formation models. These findings demonstrate that planetary systems can originate bodies with radically different compositions depending on the nature of their stars and the initial conditions of their protoplanetary disks. The study of 3I Atlas has also served to test the world's most advanced instruments and observation methods. The cooperation between NASA, ESA, and observatories across the planet has generated an unprecedented volume of data. The James Webb Space Telescope has provided extremely high-resolution spectra, allowing the identification of organic compounds at levels previously impossible to detect. The Solar Orbiter, for its part, has measured the direct interaction between solar radiation and the comet's plasma, shedding light on how icy bodies respond to the solar wind. One of the most important lessons is that interstellar objects are not exceptional rarities. Astronomers from the Vera Rubin Observatory estimate there could be millions of these bodies wandering the galaxy, crossing stellar systems on unpredictable trajectories. Until recently, our technology was not capable of detecting them, but with new wide-field survey telescopes, one new one is expected to be found each year in the coming decades. 3I Atlas will be the primary reference for studying all that come after. Isotopic analyses performed with high-precision spectra have confirmed that its composition differs significantly from that of any body in the solar system. The ratios of carbon-12 to carbon-13, as well as those of nitrogen-14 to nitrogen-15, indicate an origin in a galactic region that is younger and less enriched in metals. This implies that 3I Atlas was born in a stellar system that formed from a molecular cloud different from the one that gave rise to the Sun. For the first time, humanity can directly compare materials coming from two different solar systems. Furthermore, simulations from the Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics suggest the comet was ejected from its original system after a gravitational interaction with a giant planet. That encounter would have launched it into interstellar space millions of years ago, initiating an aimless journey that finally brought it to us. During that transit, the comet remained in hibernation, preserving its structure almost intact, like a time capsule floating in the darkness. As researchers delve deeper into the data, broader implications emerge. If the organic compounds detected in 3I Atlas are common in interstellar comets, then the ingredients of life, carbon, nitrogen, oxygen, hydrogen, could be constantly traveling from one system to another. This idea reinforces the hypothesis of chemical panspermia, according to which the fundamental building blocks of life can disperse throughout the galaxy via comets and asteroids. Although 3I Atlas does not contain life, its composition demonstrates that organic chemistry is universal, a process that repeats wherever stars and cosmic dust exist. The comet's passage has also allowed for the refinement of orbital tracking techniques. Observatories are now capable of measuring with meter precision the deviations provoked by gas sublimation. These data are used to calibrate models predicting comet behavior and to improve early warning systems for near-Earth objects. Indirectly, 3I Atlas is contributing to planetary protection, helping to understand how small natural thrusts can alter trajectories in the long term. Another fundamental legacy is the impetus for future exploration missions. Several space agencies, including ESA, have already begun studying the possibility of sending a probe to intercept an interstellar object in the future. The Comet Interceptor mission, which will be launched in 2029, is designed precisely for that, to wait in space until a new visitor is detected and then depart toward it. Everything learned from 3I Atlas will serve to plan that mission and maximize its success. The influence of this comet is not limited to the scientific sphere. It has also rekindled public interest in astronomy. Thousands of people worldwide have followed the news, images, and live streams from observatories. On social media, the hashtag 3I Atlas became a trend for weeks, and many users shared photographs taken with modest telescopes. This media phenomenon has reminded us that science can inspire collective awe without resorting to fiction or sensationalism. Researchers know that sooner or later, 3I Atlas will leave our solar system. When it does, it will return to the darkness, carrying with it the scars of the encounter with the Sun. Its hyperbolic trajectory will direct it toward the edges of the galaxy, where it will wander for millions of years before perhaps crossing another stellar system. But its passage through our neighborhood will leave a permanent mark, an archive of observations, spectra, light curves, and models that will be analyzed by future generations. The knowledge it has left behind is not just a catalog of data, it is a new way of looking at the cosmos. It reminds us that the space between stars is not empty, but full of solitary travelers, remnants of the formation of worlds that, like ours, once orbited other suns. And it teaches us that every encounter, however brief, can change what we believe we know about the universe. For scientists, the true mystery of 3I Atlas does not reside in its exact origin nor its final destination, but in what it represents: tangible evidence that the galaxy is alive, in constant exchange of matter and energy. What we today call our solar system is only a part of a much larger network where comets, asteroids and particles travel from one place to another, sowing elements and telling stories of stars that no longer exist. As the comet continues on its outward path, every new analysis reveals a little more of its history. The final data from the James Webb and the Vera Rubin will allow the precise reconstruction of how its surface reacted to the sun's heat, how much gas it lost, what fragments broke off, and how its brightness changed. In these figures hides a cosmic narrative, the birth, journey and transformation of an interstellar traveler that for an instant crossed our sky. 3i Atlas leaves us with a lesson in humility and cosmic connection. We are not isolated observers, but participants in a universe in perpetual motion. Every passing comet, every born star, every fragment of dust traveling between systems forms part of a common history. And although this visitor will soon disappear from our cameras and telescopes, its legacy will be engraved in the scientific memory of humanity as a reminder that knowledge has no borders and that even in the vastness of space, everything is connected. Thus concludes the story of 3i Atlas, a fleeting visitor that transformed our vision of the cosmos. What it taught us was not just the nature of comets, but the certainty that every fragment of the universe carries with it the echo of thousands of lost suns and worlds. Its light, which will soon fade among the stars, will continue to illuminate human curiosity for understanding the unknown.